Swayam Prabha. Digital India. Educated India.
Hello and welcome to lecture number 49 of the course Theory of Computation. This is going to be a quick but a very important lecture, right? In the previous lecture, we saw the notion of polynomial time reductions, right? So we said that A is polynomial time reducible to B if there is a polynomial time computable function f such that whenever f takes a w that is in A, it maps to something that is in B, and whenever f takes a w that is not in A, it maps to something that is not in B, right? So that's the notion of polynomial time reductions, right? So it's exactly like mapping reductions, but for the fact that the time bound, there is a polynomial time bound on the machine that computes the reduction, right? In this lecture, we will define what is NP-complete, right? So NP-completeness is a very, very important concept, as you may have heard, right? So we say that a language B is NP-complete if that language is in NP and all the languages in NP are reducible to B, right? So you want, so suppose this is the class of all NP languages in NP. So now B itself must be in NP and all the languages in A, all the languages A in NP must be reducible to B, right? So this means that B is kind of, if you can decide B, then we know that all the languages in NP are reducible to B. So if we can decide B, then indirectly that gives a way to decide any language A that is in NP, right? So two things. First of all, B must be in NP, and B, all languages in NP must be reducible to B, right? So what it means is that B, if we can we have a way to decide B, then we have a way to decide any language in NP because of this reduction that we are mentioning here. All the languages A in NP must be reducible to B, right? So because of this, it is convenient to think of the NP-complete languages or NP-complete problems as the hardest problems in NP, because if we have a way to decide this problem, let's say an NP-complete problem, then we have a way to decide any problem in NP, right? So in that sense, it is because of the reduction from all the languages in NP to B, right? So let's formalize these points, right? So there are two remarks that I make. Suppose B is an NP-complete language. Now if B is in P, meaning if we find a polynomial time algorithm for B, right? If we find a polynomial time algorithm for B, right, then we have a polynomial time algorithm for all languages in NP. All languages A in NP are solvable in polynomial time, which means that all the languages in NP are solvable in polynomial time, which means that P is equal to NP, right? Why is this? Because we already have from last class, we know if A is reducible to B in polynomial time and B is in P, then we have A is in P. So now we know that all languages A are reducible to B. Since B is NP-complete, for all A in NP, we have A reducible to B in polynomial time, right? So now because of this, the above conclusion is true. All the languages in NP are reducible to B, and we know that B, suppose we have a decider, polynomial time decider for B, right? That's the assumption. If is NP complete, and if we find a polynomial time decider for B, then we have polynomial time deciders for all languages in NP, meaning we have P equal to NP, right? So you may recall the P versus NP question that we asked a couple of lectures back. So the question was, is P a proper subset of NP or is P equal to NP, right? So we know that P is contained in NP. So is P a proper subset or is it equal, right? These are the two possibilities, right? So now if we want, like suppose it is the case that P is equal to NP, what would be one way to show it, right? How would we show that P is equal to NP? One way to show P equal to NP will be to take an NP complete problem and show that this problem is equal to, or this problem has a polynomial time decider, right? So if you want to attempt, right, I'm not suggesting or recommending to attempt, but if you want to attempt to show that P is equal to NP, this is the way to go about this, because if you show a polynomial time decider for any language, any NP complete language, automatically this implies a polynomial time decider for all the languages in NP, right? So this is one point, right? So this is sort of the significance of NP complete languages. If we can show that just any NP complete language, if we can show a polynomial time algorithm for that, that would imply the whole of P equal to NP. And since it is believed that P and NP are distinct, right? P is not equal to NP. Since that is a commonly held belief, it is very we usually do not expect any NP complete language to have a polynomial time decider, because such a decider would imply that P equal to NP, right? So whenever we think of an NP complete language, we think that it is very unlikely for it to have a polynomial time decider, right? Since it is widely believed, so I don't want to make a conclusive, or everybody does not believe this, right? P is not equal to NP. It is unlikely that any NP complete problem is in P. So whenever there is an NP complete problem, it's very, very unlikely that it is NP, right? So this is one remark. The second is that suppose B is NP complete, and suppose there is another language C that is in NP, right? B is NP complete, and suppose there is another language C is in NP, then, and if we have B reduces to C in polynomial time, right? So B is NP complete. Suppose there is another language C that is in NP and B reduces to C in polynomial time, then C is also NP complete. Why is this? Basically, to show that C is NP complete, we need to show two things. One is that C is an NP and all the languages A in NP reduce to C, right? So by assumption, C is an NP, right? So this is condition 1 is met, right? So condition 1 is met. Now we have to show condition 2. So now we have to show for all A in NP, A reduces to C, right? By assumption again, B is NP complete, right? B is NP complete. So we know that for all A in NP, A reduces to B. This comes from B being NP complete. And by assumption, we have B reduces to C, right? We have B reduces to C. So now combining these two reductions, A reduces to B and B reduces to C. So last lecture we talked about the transitivity of reductions. If A reduces to B and B reduces to C, you can compose these reduction functions to obtain a reduction from A to C. This implies that A reduces to C. So this shows that condition 2 is met. Is also met. So these are the two conditions for C to be NP complete, and thus we have C is NP complete. So if you reduce any language to show that a language is NP complete, this is one. So now this gives us another way to show that a language is NP complete. We can right? This gives us another way to show that a language is NP complete. We first show that language is an NP, and then show that another NP complete language reduces to this. So that is why this remark is kind of significant, right? So now we know several NP complete languages, right? So these are and this we consider to be the hardest problems in NP. And the thing is that many of them we have already seen in this course, even though I didn't say that they're NP complete languages. For instance, Click is an NP complete language, right? 3SAT is an NP complete language, SAT is an NP complete language, Subsystem is an NP complete language, 3-colorable is an NP complete language. All of this we have talked about many times in this course already. Now, how do we show that a given language is NP complete, right? So this gives us a way, right? If we know, let's say, so suppose we know that a certain language is NP complete. Let's say we know SAT is NP complete. Now, to show that Click is NP complete, we just have to show that Click is an NP and show that SAT reduces to Click, right? So to show that a certain language is NP complete, let's say Click is NP complete, we first show that Click is an NP and then show that a known NP complete problem reduces to Click in polynomial time, right? So this is how you usually show that a language is NP complete, right? So like that we can show all of these languages are NP complete, but then we need something to start with, right? We need so some language has to be the first language that we show is NP complete, right? So this approach works only if there is already a language B that is known to be NP complete. So what is the first language that we can say is NP complete, right? Because the conditions for NP complete seems a bit, sometimes it may feel a bit stringent, right? Because we want to show that it is an NP, that is not that hard. Usually that is the easier step. And then we have to show that every language reduces to B. So how is it possible to show that all the languages in NP reduces to that language, right? So that is not easy, or that is not straightforward. So the first language that was shown to be NP complete was satisfiability, which we saw in one of the earlier lectures. And this result, that SAT is NP complete, is commonly known as Cook-Levin theorem, and this was proved in the early 70s independently by Cook and Levin, right? So they showed from first principles that SAT is NP complete, meaning any language in NP reduces to SAT. I think we had already seen that SAT is in NP, but to show the second part, that any language in NP reduces to SAT, Cook and Levin showed this. And then once we have that SAT is NP complete, now we can show other things, like we can show that Click is NP complete by reducing SAT to Click. We don't need to reduce everything to Click, or we don't need to show that everything in NP is reducible to Click, right? Now we can take a reduction from SAT to Click and show that Click is NP complete. Now and so on and so on. Like to show that 3-colorable is NP complete, it is enough to show that 3-colorable is an NP and SAT reduces to 3-colorability, right? So and so on. So this is how we show languages are NP complete. So first we start with SAT, but and once we have a bunch of languages that we know to be NP complete, now we can reduce from any one of them, not necessarily from SAT, right? So that is the importance or significance of NP completeness, right? So NP completeness are considered to be the hardest problems in NP, and the two most important things is that if a certain language is NP complete and we show that it is in P, that implies that P is equal to NP, right? And second, if a language is NP complete and suppose B is NP complete and B reduces to C, and C is also in NP, this implies that C is NP complete, and this is used to show the NP completeness of languages, right? And that is about NP completeness. In the next lecture, we will show the NP completeness of SAT. In other words, we will show the Cook-Levin theorem, and because that's kind of a longish proof, I didn't want to continue in this lecture. So see you in lecture number 50. That's all from lecture number 49. Thank you.